Hi, welcome back. In this video entitled The Atomic Theory, we're going to talk about atoms and we're going to talk about three scientists. This you could kind of think of as the history of chemistry section. We've got some pretty big scientists that we're going to talk about and what their ideas were. So the first one, as you can see on the screen, we're going to talk about is John Dalton. In order to talk about what he came up with, we need to know what an atom is by definition. It is the smallest part of an element that still retains all the properties of that element. A lot of times we use atom and element interchangeably, but they actually are two different things. Element is the thing, the substance itself. The atom is how much of that substance. The atom is actually a unit of the element, okay? And the atom, it has to still behave like that element. So for example, a single atom of hydrogen is a gas because the element hydrogen is a gas. If we went any smaller than that atom, then we would be talking about protons and neutrons and electrons, and those are not gases. Those are particles that have charges. So the atom is really as small as you can get and still behave like the element that it came from. Alright, John Dalton proposed the law of conservation, and he came up with what he called the atomic theory. There are 4 parts to it. We've got 3 on this screen and then the next one on the next screen. And here they are. Each element is made up of tiny particles called atoms. Okay, so he establishes that atoms are a unit of elements. Okay. Number 2, elements cannot be broken down by chemical or physical reactions into 2 or more different substances. So, for example, you cannot take the element hydrogen and cause it to become anything else in a chemical or physical way. Number 3, the atoms of a given element are identical, and the atoms of different elements are different in some way. So he's saying all the hydrogen atoms in the universe are just like all the other hydrogen atoms in the universe. There's no difference between them. And hydrogen must be different than helium. Okay? And then number 4, chemical compounds are formed when atoms combine with each other. A given compound always has the same relative numbers and types of atoms. Alright, so if we look here at the figure, we see they've got this compound, whatever it is. It's got 1 red atom and 2 blue atoms. And if I want to make that compound, I have to build it that same exact way every single time. 2 blues and 1 red. We could, if we wanted to, liken that to water, which would be a hydrogen and an oxygen and another hydrogen. It's hard to write that small and still make it look good. And then over here we've got 1 red one and 1 blue one. So maybe that's like table salt. So maybe the red one is like sodium and the blue one is chlorine. So maybe that's NaCl. It has to be built the exact same way every single time if you're going to get the same compound. Okay? Alright, then we've got the atomic number, which is the number of protons that one atom has. So, for example, if I am talking again about hydrogen, okay, hydrogen has an atomic number of 1. And so that tells me that hydrogen has 1 proton. Alright? Law of conservation of mass. Mass cannot be created or destroyed during ordinary chemical reactions or in physical changes. So for example, if you take a dinner plate and you're taking it over to the sink after you've eaten and oops, you drop it and it smashes all over the floor. If you were to collect all the little pieces of that plate before you dropped it, if you collected them all afterwards and you took the mass before and you took the mass after, it has to be exactly the same. The simple act of shattering the plate did not change it. You did not destroy any mass of the plate. If I took a piece of paper and I set it on fire, that's a chemical reaction. If I collected all of the ash and I were to able to collect all of the carbon dioxide in the smoke and mass it all back together, it would equal the mass of the original piece of paper. Okay, you can't destroy that mass by chemical or physical means. And that is another idea of John Dalton. Okay, so Dalton thought that the atom was as small as you could get, okay? And of course we know now he turned out to be wrong. We have protons and neutrons and electrons and even things smaller than those now that we've found. And so he was wrong on that front, but he was right in other areas. So we kept most of what he came up with and we just threw out the wrong pieces, and that is just what happens in science. Alright, all atoms consist of these two main regions here. Okay, we've got the nucleus, and inside the nucleus you have to have at least one proton, and you've also usually got some neutral particles that we call neutrons. Hydrogen actually does not have any neutrons. It has 0 neutrons. So that's why it says usually, because I think all the other elements have neutrons in them, in the nucleus. Okay, the second part of the atom is the electron cloud, which is just a large area around the nucleus where electrons are free to zip around back and forth. Okay, so we call those three particles that I've mentioned so far subatomic particles. All right, so in science, sub means below or less than. Okay, of course, atomic is referring to atom, and then particles are just small little bits of matter. So a subatomic particle is a very small particle, and it is smaller than an atom. So these things are smaller than a single atom, which again is what made John Dalton be wrong about that little piece right there. Okay? The next scientist we're going to talk about is J.J. Thompson. Okay, J.J. Thompson was actually able to discover the charge of an electron and that an electron was actually made up of matter, that it had mass. And the way he did that was this cathode ray tube here. Okay, a cathode ray tube is like a vacuumed out chamber. Okay, there's really no air in there, and it's hooked up to a battery, if you will, some kind of an electrical source, and it's got a very high voltage, like 20,000 volts or 30,000 volts. It's very high voltage, and so one end of this cathode ray tube is negative. Okay, the other end is positive. That's what's hooked up to this battery over here, we'll say. Okay, so here's the negative end of the battery and here's the positive, and so we're going to say that this is a 20,000 volt battery here. Okay, so these electrons are going to come out of the battery, and they're going to come down here, and they're going to be attracted to the positive end of this plate. So they're going to zip along through this vacuumed out tube here. Okay, and on this end of this chamber, okay, so here's the cathode ray tube is actually this whole thing right here, and then we've got the inside of it that's causing the electrons to move towards the positive end. Okay, and on this side they've placed some phosphorescent paper, and as soon as an electron, or a charged particle I should say, because he didn't know it was an electron to start with, but as soon as a charged particle hits this special paper, it glows. Alright, and so these electrons would normally come through here, and they would go right across, and they would hit this paper, and they would fluoresce right here. They would glow. But J.J. Thompson, he started placing these positive and negative charged plates above and below the cathode ray tube. And he noticed that when he put the positively charged plate here, that this charged particle, this charge, started bending this way, and we started fluorescing up here, or glowing. Fluorescing is another word for glowing. So this beam must have bent up towards the positively charged plate. So he drew a conclusion from that. He said, okay, if this is attracted to positively charged plates, then that must mean that this thing is made up of negatively charged particles. Okay? And so those he called electrons. Well, then he did his experiment again, and this time he put what's called a paddle wheel inside of the cathode ray tube. Now, you may have seen something like this before on the back of an old steamboat engine in a movie or something like that, or maybe outside of a little cottage or cabin or something, and there's water pouring on it and it spins it, and that's what gives the electricity to the little cabin or something like that. Anyways, he put this inside of the cathode ray tube, and he again shot this beam down the tube. And when this beam hit the paddle wheel, it made the paddle wheel rotate. Okay, so as soon as this beam struck it, then the paddle wheel started rotating. Well, that could only mean one thing when he saw that happen. We know that two things that are made up of matter cannot occupy the same space at the same time. And so this beam must be made of matter, because as soon as it struck the paddle wheel, it caused the paddle wheel to move, all right, to like get out of the way. So therefore, the electrons that make up this beam must have mass. Okay, so he figured out two main things, and these are the things that you need to know. Okay, that electrons are negatively charged and have mass. Those were the two main outcomes of the cathode ray tube experiment. Okay, so you need to associate J.J. Thompson with the cathode ray tube experiment and know that he discovered electrons are negative and have mass. And finally, this experimentation led him to create what we call the plum pudding model of the atom. Okay, so back in his day, desserts and stuff would be plum pudding, all right? I don't know if you've ever heard it. There's this old Christmas song, and it's like something about figgy pudding and stuff. They ate a lot of puddings back then, okay? If we were making it today, we might call this the chocolate chip cookie model, all right? But we have to call it the plum pudding model because that's historically accurate. So there we go. This model says that all of this main space here was the positive charge, and that there were little bits of negative charge floating around inside. Okay, so there was a huge amount of positive charge in the atom, and then there was just negative charge dispersed throughout the positive. Okay, and that's what he came up with for his model of the atom. Okay, the next scientist that we're going to talk about is Ernest Rutherford. I know that that looks like Ernest Rutherford, and you will actually sometimes hear people say Ernest Rutherford, and I doubt that he cares because he's not with us anymore, but it really is Ernest Rutherford. And he discovered that the nucleus of an atom was very dense and positively charged, and he did that with his gold foil experiment. Okay, so the second scientist, Ernest Rutherford, gold foil experiment. You need to associate that with him. Alright, so here's what happened. He has an alpha particle emitter. Okay, now alpha particles are positively charged particles. Okay, and they're big, and you get them when you do like a nuclear reaction, or they're also a byproduct of X-rays. Okay, so he just shot these alpha particles, probably by using an X-ray machine. He shot these alpha particles out of this box that was open on only one side, and so it directed these positively charged alpha particles at this piece of gold foil. Okay, so gold foil, think like tissue paper that you would stuff a Christmas bag with or something, but instead of being made of paper, it's made of gold. But it's still that thin. It's thinner than aluminum foil. It's so thin if you touch it, the gold will rub off on your fingers. Okay? And so he suspended this gold foil inside of a ring of that fluorescent paper, just like J.J. Thompson had inside of his cathode ray tube. We had this fluorescent paper around the gold foil. All right. Well, the alpha particles would shoot out and go towards the gold foil, and most of the time they'd go straight through, and the fluorescent paper would fluoresce right behind the beam here where this opening is. They would fluoresce right here. But every now and then they would fluoresce at different spots on the fluorescent paper. And so Ernest Rutherford was wondering, why did that happen? In order for these alpha particles to most of the time go straight through the gold foil and fluoresce right here, it must mean that the atoms themselves, the atoms that made up this gold foil, are super small, and that they don't take up very much space, because these alpha particles are able to zip right in between a group of atoms so that they can appear on the other side and strike that paper without being deflected. Imagine that you have a line of cars here, okay? And then you get in your car and you head straight for this line of cars here, going 100 miles an hour, okay? You would be like the alpha particle, and these would be like the gold atoms, okay? It would be pretty insane for you to do that, because chances are you're going to slam into one of these other cars here, and you would be deflected off when you bounced back at some different angle, okay? But these alpha particles here, they were actually able to go straight through two of the gold foil atoms, okay? Or in your situation, two of these cars. You would be able to zip right between them and not touch either of them at all, and therefore be completely undeflected and appear here on the other side, okay? So when they did get deflected, that must have meant that they ran into something, okay? And that something either had to be really massive, okay, in order for that alpha particle to bounce back, because these alpha particles, guys, they're actually pretty massive. They're pretty big. As far as particles go, they got a lot of mass to them. So that would be like driving, you know, four-wheel drive truck, okay? And in order for your four-wheel drive truck to run into something and then for it to be the thing that bounces back, that must mean that the thing it ran into was much bigger. So maybe it ran into an 18-wheeler, and that's what made it bounce back. Well, here we've got these giant alpha particles running through, and they hit something, and then that makes them bounce back. Well, that something that they hit, it's going to have to be really massive. Or the other thing that could happen is, because these alpha particles are positively charged, the thing that it ran into, maybe it was positively charged, and so it repelled it, because like charges repel each other, and so that's what made it bounce away. So it was one of those two things. It's either really massive or it's got the same charge as an alpha particle. Alright, well, as it turns out, the nucleus inside the atom is positively charged. It's not very massive, because protons and neutrons don't have a lot of mass, but it is positively charged, so therefore it caused those alpha particles to repel. Alright, so we actually find that the nucleus is very, very small compared to the size of the atom itself, which is why those alpha particles were able to zip right in between a couple of gold atoms. Okay, most of an atom is actually empty space. Okay, and here's kind of a comparison for you. If a nucleus were the size of a single marble, okay, then the size of the atom around that nucleus would be the size of a football field. So imagine putting a marble right on the 50-yard line in the middle of a football field. That nucleus is what the alpha particle ran into sometimes that made it deflect. Other times when it appeared on the other side of the screen and right straight in line, it was somewhere else in that big giant football field. It had totally missed the nucleus. Okay? So one of the things that Ernest Rutherford discovered was that an atom is mostly empty space, and that the nucleus is very small, and that it's in the center of the atom. Okay? And that nucleus must be positively charged because it repelled the alpha particles. So that proved that J.J. Thompson's model of the atom was incorrect, and so we took Rutherford's model of the atom instead. Okay, so what are the takeaway ideas of that gold foil experiment? Okay, the nucleus is small. Okay, atoms are mostly empty space. Nucleus is in center of atom. Okay. And nucleus is positively charged. So those are the 4 things, the kind of take-home ideas that you need to know about the gold foil experiment. You need to know that Ernest Rutherford was the guy that did the gold foil experiment, and kind of be able to describe how he did that. Okay, we do have some more scientists in this history section, but I think I'm going to leave it here for today, and we'll do that in the next video. Thank you so much for learning with me, and I hope to see you next time. Bye-bye.